In this lesson, we present some fatigue models that are derived using functional equations. First, we give a model based on the independence assumption, and later we give three models assuming possible dependence among the strengths of the small pieces that make the whole longitudinal element. Finally, we discuss the problem of obtaining a consensus model. Assume that S is the survival function under fatigue of a longitudinal element of length S, that is, the probability of the lifetime t to exceed value t is given by function S, as indicated in expression 1, where p means probability, and t is the fatigue lifetime of the element. Because of the weakest link principle, the fatigue life of an element of length k times S is the minimum of the fatigue life of its k constituting pieces of length S. The figure illustrates how, when a piece is subject to an alternating load P, all its pieces are subject to the same load. One of the most important problems when dealing with the statistical analysis of the fatigue life of longitudinal elements is the size effect, that is, the influence of length on the survival function. A longitudinal element is an element satisfying the conditions. First, only one dimension is important in the behavior of the element. If the element is longitudinally divided into imaginary pieces, all pieces are charged to the same external action, stresses, forces, etc. Several models have been given in the past to solve this problem, but unfortunately, most of them are based on the assumption of independence of the fatigue life on non-overlapping pieces. This assumption states that if an element of length S is hypothetically divided into several pieces of length S1, S2, Sn, then the survival function of the element S must satisfy the equation at the bottom of the slide. Then, if independence holds, we must have what is in expression 2, which is a functional equation with a known function S. H is the logarithm of S that can be taken because S is larger or equal to 0. Since the equation for H is the homogeneous equation for any value of S, its general solution is the one given in 3, where G is an arbitrary non-negative function. In addition, since S must be a survival function, the G function must satisfy the conditions at the bottom of the slide. Here, we should abandon the independence assumptions and, making use of the functional equation theory, we should state the problem in a very different way. We should assume that a team of 3 members is required to design a consensus model for the analysis of the fatigue life of longitudinal elements. However, they are required to give separate proposals before joining together and reaching a consensus. The 3 proposals associated with the 3 members will be denoted by models 1, 2, and 3 respectively.
The next example is, I think, an interesting one. It consists of the following. There are 3 experts that want to model a fatigue problem, and they have different ideas. They want to model the survival function when you subject a piece to fatigue during a period t, and the piece has length S. So they are interested in knowing the survival function that gives the probability of failure after a period of duration t for a piece of length S. So they want to study the influence of length in the final result. The first expert established the following. He says, I think that the survival function for a piece of length S1 plus S2 is a function, a known function H, of the survival function of the 2 pieces for length S1 and S2. And that is what this functional equation expresses. This is the opinion of expert number 1.
Our first expert suggests the fatigue model 1. For simplicity, we assume n equal to 2, that is, the element of length S1 plus S2 is divided into 2 non-overlapping pieces of lengths S1 and S2. We also assume that the survival function of the element can be calculated in terms of that of the pieces. In other words, function S must satisfy the following functional equation in 4, where the function h indicates how the survival function of the element can be obtained from those of the pieces. It is interesting to see that equation 4 implies the associativity and commutativity of the H function and the dependence of the survival function S on the total length of the element. In fact, we can write what follows. The first equation proves the commutativity of the H function. We can solve for very easily if we observe that the variable t plays the role of one parameter. That is, for any fixed value of t, equation 4 can be written as the indicated functional equation, and due to the associative character of h, we can write h in terms of an invertible one-parameter function w. Substitution into 4 leads to the functional equation in the slide, which, with the indicated change of variable, leads to a family of Cauchy's equation 1 of parameter t, and then the general solution to model 1 is the one given inside the box, where f is an arbitrary function. Due to the weakest link principle and because s is a survival function, it must be non-increasing in t and s. Then, in addition, we must have the constraints indicated. The last expression in the slide gives the w function leading to the case of independence.
Expert number 2 has a lot of experience with results, and he knows the results of Bogdanov and Kotzin and some very nice lab examples of Picciotto in 1970. And here or there you have the survival function for 3 different lengths, 30, 60 and 90 centimeters. And he observes that raising these formulas or this equation or this survival function to a power, they can move from one to the other, just changing the exponent. And then the suggestion of this expert is to say that the survival function for a length S1 is equal to the survival function of the piece for length S2 raised to a power that depends on the two lengths, x2 and s1.
To know what the suggested model is, we need to solve the functional equation 6. According to Castillo et al., in 1990, its general solution is the one in 7, where the p function must satisfy some extra conditions, as indicated for s to be a survival function. Finally, the case of independence corresponds to the case of the identity function for q, as indicated at the bottom of the slide. The corresponding hazard function is the one given, which can be written as the product of two functions, one of t and one of s, as indicated, which shows that model 2 is the Cox proportional hazards model. This means that the functional equation 5 characterizes the proportional hazard Cox model.
Finally, the expert number 3 does not agree very much with the previous suggestion, and he agrees in that the survival function of for one length can be written as a function of the survival function of the other length, but not with this power. And he suggests to use a function key of this survival function and a function of the two lengths. So this is the proposal of the third expert.
Finally, our third member suggests the fatigue model 3. Based on expression 5, assumes that the survival function of one element of length S1 can be obtained from the survival function of one element of length S2 and a given but unknown function of S1 and X2. In other words, he assumes that the survival function must satisfy the functional equation in 8, which has a general solution in 9, where L, P, R, and M are arbitrary functions and L and M are invertible. For the S function to be a survival function, it must be non-increasing in T and the indicated conditions must be satisfied. The case of independence is also a particular case of this model and can be obtained using the indicated inverse of the L function. Finally, one important aspect to point out here is that equation 8 is more than a simple generalization of equation.
So we have 3 proposals for the same problem, and we need to face the problem of a consensus. They have to reach a consensus to decide which model to use. Of course, we can combine the results of the 3 experts, for example, by using means, arithmetic means or geometric means or any other kind of means, but this will destroy the properties that they want the expert the model to have. And then we are going to do is we are going to find which function satisfied all the three functional equations. In other words, we want to find the most general model that satisfies the three functional equations, and in that case, the solutions we will get will satisfy the three conditions. And you have, in a Venn diagram there, you have the proposal of model of expert 1, expert 2, and expert 3, and you have the intersection, and that is the function that you get. I think that this is a new way of getting a consensus, and the idea of maintaining and not destroying the properties, I think, is worthwhile to take into account.
Next, we discuss how to obtain the models common to models 1 and 2. To this end, we force the coincidence of solutions of both models, as indicated in the third functional equation in the slide, which implies the second one, and making the indicated change of variable, we get the expression which is Pexiter's type functional equation with general solution, the one indicated at the bottom of the slide. This leads to the solution in 10, which shows that models 1 and 2 are not coincident, but they share the common model in 11, where beta is an arbitrary positive function. As you can see, making c equal to 1, we get the independence model. The hazard function for this model is the one indicated at the end of the slide. Next, we discussed how to obtain the models common to models 1 and 3. To this end, we force the coincidence of solution of both models, as indicated in the top functional equation in the slide, which, choosing the inverse of the L function as indicated, we can write the given expression that suggests the indicated change of variable that permits to convert model 3 into model 1. Consequently, model 1 is a particular case of model 3. Finally, we compare models 2 and 3. To this end, as before, we force the coincidence of solutions of both models, as indicated in the third functional equation in the slide, which, taking logs and choosing the indicated function, can be written as indicated, that suggests the change of variable that permits to convert model 3 into model 2. Consequently, model 2 is a particular case of model 3. In this slide, we illustrate graphically the separate and consensus proposals and the common proposals associated with any group of two members. As a final conclusion, we can say that functional equations are a very powerful tool to be used in model design. We can state all the conditions to be satisfied by the desired model in terms of functional equations. Solving the resulting system, all possible and only those models satisfying all the requirements are identified. In this lesson, we have used the weakest link principle to derive a very simple fatigue model. We have also seen how functional equations can be used to derive the fatigue models associated with some properties that they must have. Finally, we have seen how the consensus of several proposals can also be obtained using functional equations. I invite you to follow the next session dedicated to laws of science, in which we show that the laws of science can be formulated in a very restricted and particular form in order to be valid.